of the equation of the circle. Again, which is this, the Pythagoras theorem. And then I'm going to link again the gradient formula. Straight line, actually. Straight line. Again, linking it with trig ratios, because there seems to be an issue with this whole concept and how they are completely related to each other. All right. So to simplify our mathematics as right now is we are just going to restrict our mathematics to two-dimensional, even though I have mentioned already that this is non-existent at all. We're going to simplify everything in two-dimensional and assume or pretend this is true, that everything is in two-dimensional, from when in actual fact objects do exist in at least 4 dimensions. I mean, 3-dimensional does at least maybe explain something, but 4-dimension is the existence of object in planes. All right. So this, you have called it for a very long time the Cartesian plane, which is based on the ideas of the French mathematician himself. So it's the XY plane, is known as the Cartesian plane. It explains or it divides numbers in 2 dimensions in an XY form across or around the point. So we understand that from this point here, which we call the origin, the X values that goes to the right are all positive, and the Y values that goes up here are positive. So in the, we call this quadrant XY, and this part here, because we have reflected on the line, X is 0. Because take note, this line is called X is 0, and this line is called Y is 0. Here we have got minus X and Y. In other words, the values of X from the origin to the left are negative and Y is positive. In fact, while we are dealing with X and Y, we should never forget the idea that these are vector quantities, and they do show a quantity and direction at the same time. So when we reflect on this line, this is now a negative, and this is also now negative. So all these ideas are connected, and this is positive and this is negative. We call them quadrants because they are divided into 4 parts, and with respect to this origin, angles around an origin, around a point, they add up to 360. And if we divide 360 into 4, it becomes 4 quarters. Where this angle is 0, we are going clockwise direction, anti-clockwise direction. This is 90 degrees, and this is 180 degrees, and this is 270 degrees, and this is 360. We go anti-clockwise by default. We rotate by default unless specified. We rotate anti-clockwise by default unless specified. We can go back and explain to engineering purposes why. And we say angles are what? Angles are positive anti-clockwise. So as we are rotating, as you have seen here, I am actually saying, maybe I should put a note here, just somewhere here, note. Angles are positive anti-clockwise. Okay, we'll get that. I mean, there's no need for me to explain the concept, the whole concept of that idea. So we are going this direction. That's anti-clockwise. We're going this direction. That's anti-clockwise. All right. So we've got this. And when we're talking about X and Y, the value of X and the value of Y here, we understand the idea that we are dealing with numbers, which we call rectangular numbers. When we're doing coding, by default, we have started, when you started your mathematics, you were introduced to numbers that are rectangular, your rectangular numbers. In fact, not just rectangular, they are also in base 10. That is why when you say 2 plus 3 is 5, in base 10. So by default, we are in that reset mode. Because remember, 2 base 3 plus 5 base 3 will not always be 7. It's not that like that. So we are in that mode. That's basically what we have. Again, now I'm going to compare this with the things that you already know. Because I want, like I said, I'm shortening the whole things that you should have done in a very long time, so that we save time here. So let me just try to make this a bit much smaller. All right, cool. So before I explain all the concepts, okay, I can draw a line here or a point. Let me choose to call this point P in here. This point, because it's on the XY plane, what we understand, it has got coordinates. I am not, of course, my graph paper here is quite accurate. It's moving 1, 2, 3, 4. 1, 2, 3, 4. So I would actually say this is 4, 4. That's what this is. And this point, it is saying I have moved to the right 4 points and I've moved upwards 4 points, suggesting that it's now a point. But the same point can be defined as a line, and we call this line OP. But then in mathematics, things don't always come with numbers, because the numbers are quite infinite and complex to work with. So we rather always use algebraic terms to represent numbers. So I would say this point is X and this is Y. So this line is called OP, and this point is X and Y. It is the same point that you can say it is equal to Y is equal to MX plus C. So it represents the same thing. Y is equal to MX plus C. It also represents the same thing, X and Y, which is a vector. So a point on the XY plane is a straight line. A point on the XY plane is also a vector. But as you draw a point from the origin, it is inclined to the positive axis. By that, I'm referring to this line here, the x-axis, which is theta is equal to 0 at this point. So it creates an angle, which I can call alpha here. And this alpha is just called the angle of inclination. In other words, this alpha is your gradient of the line OP. We'll come to that point, just not now, but we'll come to that point. So this angle is the angle of inclination, which measures how inclined the line OP is with respect to the positive axis. Are we together? So if I can complete this straight line, I would discover that we have moved X units to the right, and we have moved Y units. So suggesting this is X, this is Y, and again, this is X, creating a right angle triangle here. So OP is a scalar quantity, is the length from this point to this point, which goes X right direction and Y up direction. To calculate OP, we will use what we call the Pythagoras theorem. So OP is just X squared plus Y squared. But because OP is just kind of tedious to write, let me just call this point R. So I have a line called R, which is OP here. And the relationship between these three lines is known as the Pythagoras theorem. So we can simplify this theorem by just saying X squared plus Y squared. Take away this square root is equal to R squared. So this is the most important concept, Pythagoras theorem. Okay? But however, these points are in rectangular form. We can choose to change them based on the triangle we have created here, which is just the straight line right up to P. So we can choose to rewrite them in another fancy way. So how do I do that? I will use the angle which measures inclination of OP with respect to the positive axis. So I will start by picking up the easiest one, which is sine. Sine alpha is opposite over hypotenuse. So with respect to alpha, the opposite side here is y, and the hypotenuse is r. Cos alpha is adjacent of hypotenuse, which makes it x over r. And tan alpha is opposite over adjacent, which makes it y over x. So if you take note of that, you will realize that we actually can make certain equations here based on these three points. All right. One of the points is this also tells us that y is r sine alpha. You can just make y this up with the formula here by multiplying both sides by alpha. Then you get that. This also tells us that x is r cos alpha. So at any given point, you are allowed to change the x value and use it in other form, which is not the rectangular form. Use it in the polar form. So these are polar coordinates. These are polar coordinates. Oh, I get the spelling of coordinates wrong here. I can see that. So this can be changed to r cos alpha. Let me just make some space here. This can be changed to r sine alpha here. So x represents r cos alpha. X represents r sine alpha at the same time. So changing these values and writing the Pythagoras theorem, which is x squared plus y squared is equal to r squared, gives us something as new. Gives us r cos alpha squared plus r sine alpha squared is equal to r squared, which translates to r cos alpha squared plus r sine alpha squared, with squared both sides, of course. Squared is equal to r squared. Removing the r here creates this thing, this equation. I'm pretty sure you've used it several times as the identity. You just probably said it's an identity. No, it's not just an identity, it's the Pythagoras theorem in polar form. It's the same as that function. So we have that. I just want us to make sure that we get our facts clear in everything that we're about to start right now. So two theorems. I'm rubbing this. Two theorems so this is minus x minus y. I still need this. This is minus x and y. I still need this. So two theorems, x squared, y squared is equal to r squared. One theorem, sorry, that can be written in two ways. Is the same with cos squared alpha sine squared alpha is equal to 1. It's still the same theorem. They both represent the Pythagoras theorem in different versions. All right. Another thing that you need to know here to mention the same theorem here. If I put a compass here, I could actually put a compass. No, I don't. I need a compass. Okay. I think this is gonna work. Let's see. So I'm going to have to the technology is refusing. Okay, I think I get it now. So if I put a compass here and come here, I probably need to change and this is the point. So what's going to happen here? This is the line OP. If I rotate on this line, I'm supposed to get something. If I rotate around this line, as you can see here, I will get something that you can actually appreciate, all of you. It is a circle. It is a circle. All right. So that's it. It's a circle. You've seen that. So the locus of points around the line OP is a circle. So the equation x squared plus y squared, which you also call the Pythagoras theorem, is the equation of a circle. Of a circle around about the origin. So this theorem is broad. So these two equations, they are called the Pythagoras theorem. They are also called the equation of a circle about the origin. Okay, let's move on now. All right, another thing that you need to understand here, to calculate the gradient of this line, you can use y over x. So gradient of a straight line in this case will be, because this is y, this is 0 here. Remember the coordinates is 0, 0 here. It's going to be y minus 0 over x minus 0, which is just y over x. So gradient of this line is y over x. But if you remember what we said here, y is r sine alpha and x is r cos alpha. This takes us to the gradient of a line being equal to sine alpha over cos alpha. Okay, I should have mentioned this part already, because y is r sine alpha and x is r cos alpha. That is the reason why we end up with tan alpha is always equal to sine alpha over cos alpha. It's not anything else. It is just these trig ratios being manipulated in so many ways. And this is tan alpha and is also the gradient. So we can calculate the gradient of a straight line by using alpha. That's all. Tan alpha, tan theta, whatever you choose to call it. So everything is tied to the Pythagoras theorem. Now, the next thing is, what we can do is to find out, let me remove all this now. To find out, I can draw multiple triangles here. I can draw the same triangle in all these quadrants. The same triangle is here. It's going to be here. The same triangle is going to be here. It's going to be here. And the same triangle is going to be here. It's going to be here. Now, these triangles, they all have the same angle, alpha. But what is different now is not, and they all have the same r. Like I said before, r is just a scalar quantity, is the hypotenuse. But what you can see is this is minus x. This is now y. This is minus y. This is minus y. Suggesting that in this quadrant, to find sine alpha in this quadrant, I'll still have y over r, which is the same as what I have in the first quadrant. But to find cos alpha, I'm going to have minus x over r. And to find tan alpha, I'm going to have y minus x. What can we see here? We are mathematicians, we should see patterns. We will see that sine is positive in the second quadrant. Cos is negative in the second quadrant, and tan is negative. That is why we will put an S here and put an A here. I'll come back to the A later. If we calculate the ratios of this alpha angle here, we'll find out that cos alpha is minus x over r, is still negative, but tan alpha is minus y over minus x, which is y over x, is now positive. Sine alpha is now is negative, which is minus y over r. That is the reason why we say in the third quadrant only tan is positive. Okay. If we come to the fourth quadrant, cos alpha is adjacent over hypotenuse. So in the fourth quadrant, cos is actually positive, while sine is actually negative, and tan is also negative. That is the reason why we put a C here and an A in the first quadrant. We say all students take coffee. In short, all students take coffee, and we call it the cast diagram. It tells us about when is sine, cos, tan across the as they complete their periods. When do they change their signs? When do they become positive, negative, and just like that. Another way of explaining it, I've explained the equation of a circle and everything. Another way of linking this is also to just look at the basic graphs of these trigonometry functions that you've done. There's a lot that is linked here, and it's just a pity I have to put it all in a single lesson. This is the graph of cos theta, where this is 90, 180, 270, and 360. So the first quadrant is between 0 and 90, which is this part here. The second quadrant is this one. Third quadrant is this one. You can see the first quadrant is positive. Cos is positive. Second quadrant is negative. Cos is negative here. Third quadrant is negative. Cos is still negative here. And fourth quadrant is positive. Cos is positive in the fourth quadrant. So the diagram itself explains the cast diagram again. And while we have got this angle, we don't need to calculate any other angle in the second. This is the second quadrant, this is the third quadrant, and this is the fourth quadrant going anti-clockwise. At some point in time, I'll deal with the clockwise issues, but not now. Once we get the anti-clockwise part, we are good to go for the exams. Once you've got this in the first quadrant, you can always use it to find second, third, and fourth quadrant. For example, let's use a very basic example. I want to find sine theta equal to -half. Now, I'm not sure about the negative part here. I will ignore it for now. I will say sine theta is equal to half. Sine theta is equal to half gives me theta is equal to 30 degrees. Because it's a special angle I know already in advance. 30 degrees is in the first quadrant, which is here. Now I want to know where sine is negative. I know that sine is negative in here and in here, third quadrant. So because I've got the angle in the first quadrant, I can use it to find the angles in the third quadrant, because in the third quadrant, all angles in the third quadrant are 180 plus theta, because look here, if I continue with my straight line here, vertically opposite angles are equal. So it's a straight line, 180 plus theta. So the angles that give me -half is actually equal to sine 210. And in here, we are nearing the completion of a circle, angle around a point, which is 360 minus theta. So if I subtract 30 degrees, which was in the first quadrant, I know that the other angle is 330 degrees. These are the two angles that gives me sine theta is equal to -half. Then I can always replicate them by adding what? 360, which is the period of sine, in terms of equations. I hope this goes in a very long way to simplify the confusions that we have been encountering about trig functions. There's more to it, but I tried to shorten it up. Now, quickly looking at the idea of identities, which is there, I'm going to quickly solve them now. All these identities we are going to deal with are all emanating from the Pythagoras theorem, which I wrote in the first place as x squared plus y squared is equal to r squared. And I said this can be changed to cos squared theta. But in this case, I want to use x because the example that we are looking at has got x plus sine squared x is equal to 1. But we are mathematicians, we love to manipulate things all the time. Call this the most important thing. This is the equation of a circle. This is a Pythagoras theorem. I am allowed to rearrange this and write cos squared x is equal to 1 minus sine squared x. At some point in time, I might need to use it like this. I don't know when, depends on the question. I'm also allowed to write it like this. At some point in time, I might need to use substitute sine squared and put 1 minus cos squared. And even though you're working with these two, you can also see these are differences. So I can write this as 1 minus sine x, 1 plus sine x, 1 minus cos x, 1 plus cos x, difference of two squares. So at some point in time, again, dealing with identities, because that requires a lot of practice, but you can see that. Instead of when I substitute cos squared for 1 minus sine squared, sometimes I need to put it into a difference of two squares, simplified. Sometimes I need to use cos squared is this, I need to use this and put it in a simplified form. Sometimes I just need to replace this with a 1. It's all allowed. Depends with the question. There are times whereby, if I look again at this equation, and it's as it is here, I'm informed by the idea that we understand our reciprocal functions. 1 over sine is known as cosec x. 1 over cos is known as sec x. I can go on and on and on. 1 over tan is known as cot x. All those reciprocal functions are very important as well to remember. So now, if you are looking at this, where possibly could tan come from? Definitely it came from this identity. There's no doubt about that. It's this identity. So what I can do here to create tan, I understand tan is y over x, which is the gradient of a straight line, which is sine over cos. So if I divide everything by cos squared here, check what I'm going to get. This reduces to 1. This reduces to tan squared x. This reduces to sec squared x, which is this one. So this, at some point in time, you need to use it. Okay? How do I get cosec? I would have said 1 over sine. So again, pulling up again this identity. I want 1 over sine, so I have to divide everything with sine squared. Sine, cos over sine is cot, because 1 over tan is cot. Look here, I'll just rub it. 1 over tan is cot x, but the left-hand side is 1 over tan, which can be written as 1 over sine x over cos x, which can become cos x over sine x. So cot is also the same as saying cos over sine. So you should not forget that in general. It's all about manipulation here. So when you manipulate this, you should actually accept that this is cot squared x plus 1 is equal to cosec squared x. I mean, this is the same as saying 1 plus cot squared x, which is equal to cosec squared x. I mean, this is the same because the commutative law of numbers detects that we can change that in that form. So we actually have 1 plus cot squared x is also equal to cosec squared x. That's equation number 5. So we can manipulate this in so many ways we want. All right, is required here in so many ways depending on the equation. Now, I'm going to deal with this 2, 4, and 5 again. You're not restricted to just thinking about them in this way. Look here. 1, which is we know is cos squared plus sine squared equal to 1, can also be written as sec squared x minus tan squared x. The same one can also be written as cosec squared x minus cot squared x. I can call this equation number 6 and this equation number 7. So I've got more than enough manipulations I can do when I am faced with these identities. Just to take your look at number 6, using 6. 1 is also the same as sec x minus tan x in bracket sec x plus tan x in bracket, because this is a difference of two squares. I can do the same with number 7. I can do the same with number 7 as well, to get cosec x minus cot x, cosec x minus cot x again. So it all depends with the question at hand. I hope I've answered a lot that you've been struggling with here. Now, these questions are very, very, very tricky. Not trick, but they need you to pay attention. So I'm going to solve this question using the most important tool in trigonometry, which is the cast diagram. So what I understand is all students take coffee. Sine is positive between 90 and 180. Tan is positive between 180 and 270. I really don't like to use degrees. I prefer radians for accuracy purposes, but that's fine. And this is 0 to 90. So tan can only be negative in 2 quadrants. By now you've realized that. So tan can only be negative in 2 quadrants. Can't be negative in all quadrants. It can only be negative in this quadrant, or it can be negative in this quadrant. So let's use A here. So this is our A, and this is still our A. If tan is negative in the second quadrant, and we know that it is opposite over adjacent, the opposite side is the y value. So y value is positive here, as you can see. So 5 is the positive value, and the adjacent side x is negative. X is the negative value. If tan was in the fourth quadrant, opposite value is this one with respect to A. So this will be the negative value, and this will be the positive value. But which one of these two is the correct one is the second statement. A is obtuse, and we all know an obtuse angle is an angle that satisfies this requirement, suggesting that it's the second quadrant. So this is not there. So the actual trig ratio representing these two questions is this part. Doing a Pythagoras theorem, you actually, I want to believe this is 13, even though I'm not sure, but yeah, it should be 13 anyway. It was 144 minus 25. 144 plus 25 is 169. Yeah, that's correct. Now, that's done. So exact value for sec is based on this triangle, which is sec is just 1. Okay, I might just write sec A is 1 over cos A, and 1 over cos is adjacent over hypotenuse, which is minus 12 over 13, according to this triangle, which turns out to be just minus 13 over 12. That's your answer. Sine is opposite of hypotenuse, is 5 over 13. But if you look, if I used the quadrant in the fourth quadrant, the answers I'm going to get are quite different in terms of their signs. So you need to be very careful as far as this is concerned. All right. As you can see here, I'm going to do A and leave B as your form of practice. This is another important thing I need to emphasize to candidates. You're about to write examinations final. When you start your arguments mathematically, you communicate mathematically with the examiner. So you want to prove that this is equal to that. So it's either in an equation, we've got two things written here, left and right. So normally you want to start with the left-hand side. The left-hand side is going to be equal to cosec to the power of 4 theta minus cot to the power of 4 theta, just like that. So you've got to present your argument in that manner, not just to write randomly. I expect students to write it in this order. Now, like I said, what we see here is cosec and cot. It might not show like we are getting somewhere to the right-hand side, but trust me, it is getting somewhere. First of all, the exponents are even numbers, suggesting that every even form number is a square number. So I mentioned it when we started. So I can do this. You all agree with me, I've done a difference of 2 squares. And if I go back somewhere in the difference of 2 squares, you will see equation 6 and 7 here. Cosec x minus cot squared is also 1. That's where it is coming from. Cosec minus cot is 1. So this equates to 1. And this is cosec squared theta plus cot squared theta. So I can still continue with the left-hand side. Now, I'm sure where I want to go, I just want to see cos. I don't want to see anything else other than that. So I have to change this. This is cosec. So what is our cosec, by the way? It's 1 over sine squared theta. What is our cot, by the way? Is cos squared theta over sine squared theta. The denominators are the same. So the left-hand side, I'll continue writing it as the same denominator, which is 1 plus cos squared theta all over sine squared theta. A careful examination of where we are. We now have 1 minus. How did it come to? I'll take you back to what we did here. Sometimes when cos squared is here, I might want to replace it with 1 minus sine squared at some point in time. But right now, cosec sine squared is here. I'm going to replace it with 1 minus cos squared theta, which is equal to the right hand side, and as required, it has been proved. But what is very important is not just the use of the trig identities here, is the presentation. I started my argument like this, and I went with an equal sign, and I ended up here. I expect to see students putting their arguments in a very mathematical way. I can prove again using the right-hand side. It is perfectly allowed because an equation is satisfying the law of conservation of numbers that says left is equal to right because there's an equal sign in between. So we understand there's the same thing. So I can work from the right-hand side as well and go to the left-hand side. That will be your own homework. Well, maybe let me just do this one quickly to aid understanding. So the right-hand side, I'll start by writing it like 1 plus cos squared x all over what? All over 1 minus cos squared. This is not x theta. I was thinking of a very long way, but while I was thinking about it, I just saw something else. I think this is going to work properly well. 1 over sine squared theta cosec squared theta over sine squared theta. And this is cosec squared theta plus cot squared theta. But I remember very well that if I multiply this with 1, it doesn't change. I just thought about that. But what is this? In respect to this, it is cosec squared theta minus cot squared theta. I just thought about that. And expanding this is a difference of 2 squares. Definitely gives you cosec 4 theta minus cot 4 theta. I forgot to say equal to the left-hand side as required again. That's perfectly okay. This is your own way to look at it and see how best you can work this through. I'm going to do the last one here, and hopefully this answers everything else. Again, cot theta is minus root of 3. I want us to draw this. Cot theta is minus root of 3 can be converted to 1 over tan theta, which is minus root of 3. If I do my mathematics right here, I'm pretty sure I've got it right. Don't think I made it mistake. Tan theta is minus 1 over root of 3. Of course, the rationalized, this gives you minus root of 3 over 3. That's all right. But what do we know about tan? Tan has to be negative in here again. Or tan has to be negative in here. So, but it can be for the specific question. We're using theta, so let me put theta here. And then I probably needed to use a different color here, but okay, let's see how it goes. Okay. Yeah, that's right. And if I do the trig functions, I mean, let me keep it simple and use this one. It's opposite of adjacent, which means this is 1 and this is root of 3. But there's a minus here. So which one is minus? It's not this one. It's not this one. This one is positive. We know that's our cast diagram. That's our XY plane. The Y values are positive here. So this is this one. And if you do your Pythagoras theorem correct here, you are actually going to get x squared plus y squared